In this video, we're going to begin our lesson on implicit differentiation. The functions that you've seen up to this point, you could write y in terms of x. For example, this equation, y equals 3x squared minus 5, we always used x as the independent variable. We plugged numbers into it, calculated, and then our answer was the y value. And if you pair up all the x, y pairs that satisfy that equation, you can draw a graph that goes through all of those points. A lot of our graphs, we are able to see that they pass the vertical line test. For example, just this equation, 3x squared minus 5, if we take this equation, we will get a parabola that has a y-intercept at -5. And if we look at any location on this graph, we can put a vertical line through it and only strike once. So graphs that pass a vertical line test are functions. Well, not all graphs will do that. For example, the unit circle. The unit circle will not pass a vertical line test. And that's okay. This is our way to get the rate of change on any graph, whether it's a function or not. Towards the bottom, let's look at halfway. We're used to seeing explicit form like y equals 1 over x. We could rewrite that as x to the -1 power, and it makes it fairly straightforward when we take the derivative. The derivative of y with respect to x is going to be a -1. Take 1 away from your power, -1 times x to the -2, or -1 over x squared. This is pretty good strategy if you can isolate y, but we're not always able to isolate y. For example, the unit circle, and let me pencil that in. If we had x squared plus y squared equals 1, if you were to isolate y, we have a y squared. In order to isolate that, we would have to take the positive and negative square root of 1 minus x squared. A circle won't pass a vertical line test, but it's still possible to find the rate of change anywhere on it. And this is where implicit differentiation comes in. If you need to pause and read this part of the slide, please do so. I'm going to scroll down and let's look at some examples from your e-text. The derivatives we've been taking so far, the dx and our variable x, the variables agree in the notation. And when we take the derivative, we just simply get 3x squared. If the argument isn't the same variable, like we want to take the derivative with respect to x, but our function is y cubed, you still take the derivative using power rule. It's 3y squared. But we're going to also have this dy dx notation as u prime. It's part of the chain rule. Part C, if you have a combination of x and y, remember when you take the derivative with respect to x, you take the derivative as always. Derivative of x is 1. If the arguments or variables disagree, you still take your derivative. The derivative of 3y is 3, but you also have this dy dx notation. This one we have both letters, but they're a product, so we have to be careful to use product rule and keep in mind our chain rule in the implicit differentiation. For example, derivative of the first times the second. It's written backwards in the e-text, but we know how to do it in class. plus the first times the derivative of the second. Again, it's out of order, but with product rule, it's okay because adding can be done in any order. Quotient rule, you got to really watch the order. So x times the derivative of y squared, that's going to be 2y dy dx. We'll see this notation. If the variables don't match, be sure to use this notation. Plus y squared dx of x. Those match, so the derivative of x is just 1. And then finally, we clean all this up. We get 2xy dy dx plus y squared. We did several examples in class today. Let's remind ourselves of those. Please zoom in for us. There we go. All right, so let's start at the top left. We have the equation 3x squared minus 7y squared equals 1, and we're going to solve for dy dx. First term, the variable is x. That matches. That derivative is 6x. The second term has a y. That doesn't match. That's okay. Let's take the derivative. It's negative 14y. We just have to remember dy dx. It's the chain rule for a different letter. You could also write this as y prime. I use the dy dx. You see it quite often. Let's solve for this dy dx. I'm going to take this term across the equals. It's negative here on the left. When I move it to the right side of the equation, it becomes positive. And in order to isolate dy over dx, I'm going to divide both sides by 14y. 6x over 14y reduces to 3x over 7y. The example at the top right, when we take the derivative, our first term is solely based upon x, that's 5x to the fourth. In the middle, we have a product of an x and a y. I'm going to pull this minus sign down and start a bracket. In the bracket, I want to do product rule. Derivative of the first times the second plus the first times the derivative of the second. The derivative of y is 1 dx. Third term is strictly a y variable. That's derivative is 2y dy dx, because again, if your letter is different, you have to use chain rule. Any constant has a derivative of 0. Distributing the minus sign, we have 5x to the fourth minus y minus x dy dx plus 2y dy dx equals 0. Solving for dy dx, any term that has a dy dx, I'm going to leave on the same side of the equation. Any term that does not have it, I'm moving over. This negative y, when it's moved, becomes positive y. 5x to the fourth, when it gets moved, it becomes negative. Once you've sorted out your dy dx terms from the non-dy dx terms, factor out the dy dx. That'll leave us with a negative x plus 2y. It's totally fine to write 2y minus x if you like. Once you've factored that term out, divide both sides by your brackets, and then you've got dy dx. Top left, we have the product of x to the fourth and y to the eighth minus y equals x. This first term is going to require product rule. It's the product of x to the fourth and y to the eighth. Using product rule, we have derivative of the first, that's 4x cubed times the second, plus leave the first one alone, and the derivative of the second, that's 8y to the seventh dy dx. Middle term is minus y. Its derivative is minus 1 because it's a y variable, dy dx. And then finally, the derivative of x is just 1. I'm going to move 4x cubed y to the 8th to the other side of the equation. It's going to go from positive to negative after being moved. That leaves our dy dx terms together. Factor out dy dx. That will leave you 8. I moved it out front just so it wouldn't be stuck in the middle. 8x to the 4th y to the 7th minus 1. And that's still equal to our right side. Solving for dy dx, divide by what's in the bracket, and this is your derivative. You can find the rate of change anywhere on a graph, even if it's not passing the vertical line test, because you have an x and a y value, so you can sub an entire point in instead of just an x coordinate. Let's look at the top right. We have a product of x e to the y. That's going to be derivative of the first, derivative of x is 1, e to the y, plus, now we leave the x alone, derivative of the e to the y is e to the y. The difference in the variable requires us to chain it with dy dx. Our middle term only has an x, its derivative is negative 11. Third term, 7y, its derivative is 7, dy dx. Derivative of any constant is 0. Collecting our dy dx terms together and moving our non-dy dx terms over, the negative 11 becomes positive, e to the y becomes negative. Factor out your dy dx and divide by x e to the y plus 7 on both sides, and that gives us dy dx equals 11 minus e to the y over x e to the y plus 7. And our final two examples of the day, we got to these two, and I wanted to bring in some trig. Let me move it up just a little bit. There we go. There we go. Sine of x, we only have the x variable. Its derivative is cosine x. The next term has a y variable. The derivative, we're going to use chain rule. So our derivative is going to be negative 4 sine. Remember, it's the derivative of the outer part. Inside left the same, times the derivative of the inside. Well, since the inside has a y variable, its derivative is 4, but we don't need to forget the dy dx. This 4 and this 4 I'm calling 16. I'm moving all of this to the right side of the equation, so it'll go from negative to positive. 16 sine 4y dy dx. Dividing both sides by 16 sine of 4y gives us dy over dx. And finally, y equals sine of x times y. In class, I mentioned that if this y in the angle wasn't there, it's one that we're used to seeing. It's y equals sine x. Your derivative is y prime equals cosine x. But because of that y in the angle, we're going to have to be careful. This is still going to be y prime. It's 1 y prime. That's written as dy dx. It's fine. Now, on the right side, we're going to have to use chain rule. Derivative of the outside is cosine. Leave the inside alone. Now, when we take the derivative of the inside, because it's x times y, we have to use product rule. Derivative of the first is 1 times the second, y. Plus, leave the first alone, x, times the derivative of the second, which is 1, but because it's y, dy dx. Distributing this cosine of xy into these two terms, I did them in color code in class, so it was easier to keep track because it gets messy after a while. The orange distribution, it's the first jump. We have a y times cosine xy. I left it in orange. Plus, now on the second jump, I did it in blue. We have x cosine xy dy dx. I left that little term, that dy dx term, in black, but I wanted to color code the distribution part of it. The left side has dy dx. This last term on the right does too. When I move this blue term over, it's going to go negative. Factoring out dy dx, I'm left with my 1 and a minus x cosine xy. Solving for dy dx, I divide by my terms in the bracket, and I've got y cosine xy over 1 minus x cosine xy. And if I needed to know, for example, this graph of the original problem, if we were to look at a graph and I needed to know the rate of change at a specific point, I have x's that I could plug the x coordinate in and a y that we can plug the y value in. In the next video, we're going to do some of those. This video, we're just getting an intro on how to take derivatives implicitly.